Hello everyone, I'm Chris McIntosh. I help teach these statistics courses. I wanted to go over the week 7 computer assignment with you. So the objectives for this week's computer assignment is to conduct an independent t-test in Jamovi, interpret the results for an independent t-test, report the results for an independent t-test, and interpret a base factor for an independent t-test. You want to download and open the data set in Jamovi. The data set is posted in Canvas. And once you have the data set downloaded and opened, it should look like this in Jamovi. Let's go to Analyses, Exploration, Descriptives to get some results. Result page started. And you want to click in the results and add your name to the top of the page. So you want to use the statistical analysis checklist to help you conduct an independent t-test. And this is what the checklist should look like for week 7. And so that's what the tool you want to use to go through this and what I use to go through this. So answer the questions in section number 1, study information. So for section number 1 for study information, gives us the big picture. And I have those listed on this slide. So the study purpose, this is a learning exercise. All the data are fabricated and results are not generalizable. Seems a little silly to go over this for an assignment, but I want you to get in the habit of thinking about a study and the context of the data that you're working with. So just get used to running through these kinds of things in your mind before you work on any kind of analysis. The research questions, and there was kind of a question stated in this data. I'll mention this. These data come from your HEVI text in chapter 9 about students t-test, and they're the data that are listed on page 135, age and drug screen status for patients under age 25 in a trauma center. So HEVI did give a bit of a research question, and the question was, is there a difference in mean age in trauma patients age 25 and younger who have a positive drug screen and those who have a negative drug screen? And there was no hypothesis specified. The study design, there wasn't really one described here, but groups are compared. There didn't seem to be any random assignment to groups and no manipulation of an independent variable. So this would probably be classified as some kind of a pre-experimental descriptive design. Ethical considerations, none were described here. Data collection and handling, none were described here. Answer the questions in section number 2, data set information. So what are our variables and level of measurement? You would get that by looking at Jamovi. Click on the data tab. So we have an age variable, and these are all numbers. So I'd call that ratio level of measurement. And then we have a drug screen variable with zeros and ones. So that should be nominal. And we can just double check that these are set correctly in Jamovi. Age is continuous. That's correct. Drug screen is nominal. And I would suggest adding the names of the levels in here, because right now it just says 0 and 1. And if you're used to doing this all the time, usually, you can keep that separate in your head. But I would go ahead and add in 0 is a negative drug screen, and 1 is a positive drug screen. And you'll see that it still has 0 and 1 there, but it did change those to say negative and positive, and it will make the output more easily interpretable if you go ahead and add those in right there. Data accuracy. So let's look at some descriptive statistics just to see if everything seems as it should. And this is a small data set, 20 entries. I mean, we can look at this, easily and go, okay, all the data are there in both of these columns. I don't see anything that looks out of the ordinary. But if we click on our descriptives, then let's go ahead and put our age in the variables box, and let's split it by drug screen. And let's just double check some statistics. So because we have a continuous variable, a mean is useful to get, standard deviation, minimum and maximum, and we are going to be doing a t-test, so I am going to be concerned about a normality assumption down the road. If you missed it now, then you could come back later and add it, but let's go ahead and we're going to add skewness and kurtosis to these descriptives, and a normality test, and we can click on plots, and for a continuous variable like age, histogram and box plot would be the thing to look at. So let's go with that for right now. Let's go ahead, and since we are looking at drug screen 2, let's just get frequency tables and let's see what we get here. Okay, so we see age split out by positive and negative groups, and this is good just to kind of orient ourselves to the data. So it looks like we're running somewhere between 15 and 25, and then we have some lower ages over here on the negative group, and then some higher ages on the negative group. There's our box plots. We can see we have quite a bit bigger box plot on the negative group, and a smaller box plot on the positive group, so there's a lot more variability in that, and we probably should see that in our descriptive statistics. We can see we have our means there, and then our standard deviations. The negative group is 8, and then positive group is 3, so quite a bit more variability in the negative group than the positive group. And I don't really see that a separate frequency table came up. So let's go ahead and just do another thing so we can get frequencies for these drug screens. So I'm going to go to Analysis, Exploration, and Descriptives. And let's go ahead and get drug screen. Over here is a variable with a frequency table. And we can see we have 14 and 6 right there. I'm going to go ahead and take away the mean and median and the standard deviation, min and max. I just wanted the frequency table so we could see how many were in each group. And we can see we only have 2 groups here. If we had any spelling errors in groups, or you would see extra groups there. So and we have no missing data in anything. So our data looks pretty good. The ages all seemed reasonable. We didn't have any 500-year-old people. So data accuracy all looks pretty good. data manipulation. We don't have anything we're calculating in this data set, so nothing there. We didn't have any missing data. We didn't see any outliers. And we just kind of went over the descriptive statistics right there. So we're good on our data set information. Okay, answer the questions in section number 3, test information. And this is kind of information relevant for a t-test. So you should have updated your checklist, and this will get into some particulars on the t-test with a null and alternative for a t-test, and how we're going to report these statistics. We're going to do a t-statistic with degrees of freedom and a value, and then a p-value with a value, and our decision. So I think, yeah, we'll go with that for right now. Okay, so let's go ahead and do the select which test in Jamovi, and we know that you should have added the t-test to your which test should I use. And on the one variable tests, when we just have a one sample t-test and we're comparing our sample with the known mean, or a mean that we want to test against, that's a one sample test that's relevant for an interval and ratio level of measurement. And then you should have added a independent t-test for interval and ratio up here. So if you had oh, I put that in the wrong place. Let's go fix that right now. I'll fix it later. Well, I'll fix it now. Won't hurt you guys to see. This is a GitHub, and our outcome variable should be interval and ratio, and our independent variable is nominal. So these two should actually be down here. So I'm going to go fix that in this table. And this table looks ugly. This is Markdown. But I'll just fix it really quick. So let's grab our independent t-test. And I have these color markers here to make it a little bit easier to read. And so we want our outcome variable with interval and ratio with the nominal. I'm going to paste those into there, and let's get rid of that. And hopefully I didn't mess anything up on the table and it's going to look okay. Okay, that looks better. So our outcome variable, our dependent variable, and this should look okay for you guys because I just fixed it, so it should show up, is continuous, interval and ratio, and our independent variable is nominal. And it's two groups, specifically independent t-test, and if you have a problem with normality, you can do a non-parametric test, and the non-parametric alternative for an independent t-test is a Mann-Whitney U-test. So we added that there in that table. Glad I double checked that. But let's go into StatCat. You should have added this last week if you're in the modules, but if you didn't, you can go to the Jamovi library and look for the module, and you're looking for this one called StatCat, and then it will appear on your screen here. And again, we're doing relationships, prediction, and group comparisons. T-test is for group comparisons. And we have our dependent variable, which is our outcome variable, which we're looking at age as the continuous variable. And our independent variable is drug screen with groups. And you'll see that it tells us that we should have a 2-sample t-test, which is the same as an independent t-test. So all of these statistical tests have several names you'll see used in different areas and fields, and it's good just to get used to knowing the different names, and talks a little bit about assumptions that we're going to talk more about. So a couple options there, and then if it's normality is violated, the Mann-Whitney U-test, and we do see a little scatter plot, nowhere near the data we saw last week with the chi-square, but we have our negative and positive groups and some ages falling in here. So handy to see a little scatter plot. So in case you were need to know in the future, StatCat can help you predict a test. Okay. Independent and dependent variables and levels of measurement. We looked at that already when we were doing our data screening, so we're good with that. Test assumptions. So for an independent t-test, I forgot to include this in an assumption last week with the chi-square test, but this assumption also applies for that. So, and the books did not really emphasize this, so I just wanted to mention this to you guys. One assumption of all the statistical tests is that your sample is randomly selected from a population. And boy, I am batting 1,000. I just saw that typo in this slide. Let's fix that while I'm here. Okay. So your sample is randomly selected from a population, and this seems like a small assumption, but in reality, this is an assumption that's violated to some degree or another by almost every statistical test. And the reason is it is really hard to actually get a random sample. And so in this particular example, these were people that came in for an emergency, a trauma, and so that's not a random selection, that's a convenient sample. And even in very large studies, maybe you're using voting records. Well, that means that you're got people that registered to vote, and then you're missing all the people that didn't register to vote. So it's not truly random. You've pre-selected for some set of people. If you do phone numbers, you're pre-selecting for people that have a phone. And so it is almost impossible to get a truly random sample. So every statistical test violates this to some degree or another. And so that's a challenge in when we're trying to draw inferences. So I just want to point that out to you guys and have you think about that a little bit, and what the implications might be to the applicability of our results to our inferences we can draw about a population. Another assumption is that we have independent observations. This is something that you know from the study design, and we're assuming that this is true, yes, here. Normality, and so let's go and check normality for our data set. So to do that, we're actually going to go ahead and get some t-test results, because it will help us do some normality checks. So we're going to go to analysis t-tests and independent samples t. And our dependent variable is age, and our grouping variable is drug screen. And we know that we want to look at, let's go ahead and just put our assumption checks there. And so we're not ready to look at our test results yet. We're just focused on assumptions. So normality, we have this Shapiro-Wilk test, and Jamovi gives us that. SPSS does another one called the Kolmogorov-Smirnov test, but the purpose is the same. We see that this is a non-significant result, meaning that we don't differ from normality, and that's what we want to see. Um, so, uh, and this normality assumption, this is where statistics is all shades of gray, and real world data are never going to be perfectly normal. If something is perfectly normal, you might start to wonder if it's fabricated. So you're going to violate this assumption to some degree or another, and then the question is going to be, how good is good enough? And so there are some good guidelines that we can use here. One, we can have this test, and we're not significant, so that's a good indication that we're good enough. We did look at our histograms here, and these aren't like stellar looking data as far as normality goes. And so, I might wonder, but we just did this other test. Just looking at a histogram was called an eyeball test. You just kind of gauge it. And a lot of times if the histogram looks pretty good, then you have a good indication that it's going to be okay. The thing about normality and t-tests is normality involves both skewness and kurtosis. And in reality, the kurtosis part is not quite so important when it comes to t-tests. So sometimes these inferential tests, testing for normality, if data are kurtotic, these can be significant. And in reality, we aren't worried so much about the kurtosis. So sometimes, even if it's a significant Shapiro-Wilk or Kolmogorov-Smirnov, I might just go look at the skewness, and you see we have the skewness and the standard error of the skewness. And if you divide the skewness by the standard error of the skewness, if you start getting a value of 2 or greater, because it's a kind of a standardized result, you might be concerned about violating that assumption. And here we have negative 0.56 divided by 0.59, which is close to 1. Again, not a problem. So we're going to pass that, but there's several ways you can check this. And another thing to consider is your sample size. When you have a large sample size in a t-test, your normality assumption gets less important. And then the question is, well, what's considered a large sample size? And usually it's 30 and above. If you're above 30, then your normality assumption, even if you violate it somewhat, it's not quite such a big deal. So a lot of shades of gray here to consider. But in the long run, a small sample size, you really worry about normality. And we have 20 of the observations. This is considered small, and we don't seem to have a problem here. So that looks good. Okay, our other assumption here is homogeneity variance, Levene's test. So you learned about another test this week called Levene's test, and in our t-test assumption output, we're looking at this Levene's test, and we see we have a p-value of 0.004. So, and the Jamovi creators are kind enough to give you a reminder here, a low p-value suggests a violation of the assumption. So if we're significant on this Levene's test, that means that we're significantly different, that our variances are significantly different from each other. And that jives with what we saw in our descriptive statistics when we looked at our standard deviations. One group had 8 and another group had 3. So we knew that there was quite a big difference here. We can see that in the box plots. One group is the box plots quite a bit shorter than the other group, so there's a lot more variability here. So we're actually violating our Levene's test assumption, and we learned that there is an alternative. Rather than just interpreting regular students' t-test, we want to interpret Welch's t-test. And so if we click the box for Welch's t-test, now we can see that we have 2 lines here, and we want to make sure that we are working on the bottom line. And in the book, and this is a good thing for you guys to understand, that different statistical programs will give you different information by default, and sometimes they make it look a little bit different. So you see as an example of some SPSS output in the book, and if you look at it closer, you're going to see the information is the same. I actually was trained on SPSS, and SPSS never bothered to tell us that that was actually a Welch's t-test that it was giving. I just knew it was an adjusted value to interpret that line when we violated Levine's homogeneity of variances test. But there's a name for it, Welch's t-test. So we're going to make sure that we're going to interpret that line right there. And then our null hypothesis significance testing steps, we state the null and alternative hypotheses. The null is there's no difference between group means. The alternative is there is a difference between group means. Our criteria of rejection, and we'll be using this pretty much all semester, but it can be different sometimes, so is alpha 0.05. And then we're going to calculate our test statistic, and we did that, getting that. And then we're going to look at our p-value here, and we see that our p-value is 0.212, which is above our alpha level. So we would fail to reject this null hypothesis, and we'd conclude that there is no difference in group means, certainly not a statistically significant one, according to this test right here. There's no real post hoc tests with t-tests. And then our effect size, over here under additional statistics, we're going to get our effect size. I'm going to go ahead and get a confidence interval here, and let's get descriptives and descriptive plots. So we can look at this full information here in Jamovi, and this is quite a nice thing in Jamovi that you can just add extra things in and the output updates. I don't know what SPSS is like currently, but over 10 years ago when I was using it, anytime that you change something, you had to go rerun the test, and it would tack the new output to the bottom, and you'd get this really long output, and you'd have to scroll to the right section with the version of the test that you wanted. So I kind of like this ability to adjust our output right here live. So we see we get Cohen's D over here, and we were definitely interpreting Welch's because we violated our homogeneity variance assumption. And we see here we have a D of negative 0.530. The positive and negatives don't really mean much. It just depends on which group gets numbered 1 and which gets numbered 0. So, but 0.53 would be like a medium effect size. That is interpreting the test. And all right, let's move on to see what else I put in here. Okay, so I wanted to talk to you guys a little bit. As I looked through this example in the Heavy text, I had a couple thoughts about it, and I think this is a good opportunity, and this is part of why I chose to look at this particular data to talk with you guys about it, because I think this is useful to think about. So whenever you're doing a statistical analysis, you really want to ask yourself, what is the story the data are telling you? What do these numbers mean? They're not just numbers, there's actually a meaning to this. And the big question in all of statistics is, so what? Why is this important? And so this is a good opportunity to think about this a little bit. Statistical analyses need to be interpreted in context. So if you can't take this back to what this means in the real world, then you're probably missing something pretty important. So some questions that I had regarding this example is, why are drug screens being conducted on toddlers and young children? When we looked at this data and we saw these ages, we have like 2 to 8-year-olds, and I just wondered to myself as a nurse, why are they conducting drug screens on toddlers and children? Because in my mind, how would a toddler and a child get access to drugs? I assume they're screening for illicit drugs. It wasn't described well. If this were a real study, you'd want to be describing that really well. So that might be something that you would notice and question about that study. And this is a textbook example. I'm not criticizing the author on this particular part, but you really should be trying to connect these dots for yourself. And so I really question that. If this were a study design, I'd be very curious to understand what were their inclusion and exclusion criteria for this study, and why did they choose those particular inclusion and exclusion criteria. So in my mind, truly, I question why these young children would be screened for drugs, and would the reason that they're getting drugs be the same as the reason that these older people were getting drugs? And I don't think so. And so I would question this particular study design. And then, just as an example, I wondered why the author created a frequency table for age. And the author did not explain that, and I've worked with you guys to try and talk about the descriptive statistics and plots that are relevant for the different levels of measurement. And typically, this was only 20 participants, so it didn't make a very big table or box plot. But if this were 100 or 1,000, and we've worked with a couple data sets that were like that, that would be insanely large. And there really wouldn't be a good reason unless you had a reason for looking at those frequencies like that. And so I wanted to just share with you guys, even though that's in your textbook, do not follow that example in your own analysis. If you have a continuous variable, you really shouldn't be generating a frequency table or doing a box plot on those. So I especially wanted to mention that to you because it is in a textbook, and we all just kind of assume that what they do in a textbook is something that should be copied. Don't copy that in your own work. So, and unless you have a reason to deviate from a standard practice, just don't, do it, because those tables would be problematic. Yeah, that's what I'm just going to tell you about that. So we saw something new. I did lecture with you guys, and I'm going to go back down to our t-test. And we learned about the Bayes factor. And I was not taught about these in my doctoral program, but and the tools to do Bayesian statistics were hard to use. But as you can see here in a quite easy to use program, we now have a checkbox that we can turn on to get a Bayes factor. And so I thought it was worth mentioning to you guys that this exists. And Bayesian statistics is an alternative to null hypothesis significance testing. And as you saw in your reading, another word for that type of statistics is called frequentist statistics. And the idea behind it is, if you did that type of study over and over and over again, you would come to the idea of the central limit theorem is you would come to see what the true population values were from many repetitions. And conceptually, that makes some sense, but in reality, I've never seen a study conducted 1,000 times. It's very rare that we see studies repeated twice. And so that's a bit of a conceptual issue. And so Bayesian analysts, highlight the fact that in reality, we're just kind of updating our beliefs. And so I think there's some merit to that idea. And so this idea of a Bayes factor is, with the Bayesian statistics, we actually can generate some evidence for one hypothesis or the other. And as we talked about before, in null hypothesis significance testing, we're just assuming that the null hypothesis is true, and then we generate this p-value to go, oh, if it's extreme, then maybe I should reject the null hypothesis, and that's what you do. The Bayes factor actually gives you evidence for one hypothesis or the other. And I'm going to shut a door because my dogs are being noisy. Okay, so, and you'll see it says Bayes factor, and then it has a little 1, 0. So we've been using 0 as our null hypothesis and 1 as our alternative hypothesis. And this is showing this in the format that what's the evidence for the alternative hypothesis? It put the 1 first, and you see 0.567. And I, looking at the Navarro text, I kind of like Navarro's convention that to report these as a whole number. And if we were going to switch this around and do the 0, 1, rather than looking at this as a fraction, and we'll just convert this, because all you need to do is take the inverse, and we could get this really fast in Google, equals 1 over 0.567, and this Bayes factor would be 1.76. And we learned from our text that there are some general guidelines for strength of evidence, and that would be pretty modest evidence in favor of the null hypothesis. And that matches what we had decided to fail to reject the null, but it's not a slam dunk. Because, you know, to get to any strength of evidence, we're looking for values of 20 or more on that. So since we have this, this data in the computer, I thought, we could look at this a little bit. What would happen if we took these children out of this analysis? Because I question the applicability of including children in a study looking at drugs and trauma. And so we can actually do that pretty easily here. If we go to data, we see we have filters, and we're going to look at, I want everybody that's over the age of 12 included in here. So we're going to say age greater than 12. And then when we click outside the box, if we type things correctly, you'll notice that Jamovi has now put a red X next to the younger participants, the children, and a green check mark to all the others. So that means that the results we're now seeing only include the teens and young adults that are part of this study. And so what you'll notice is that Jamovi, if we went back and looked at things, and I think that it's easiest to see with the box plot, these box plots are much more similar to each other now, and everything gets changed based on this filter. And you can turn this filter, you see this little active button, on and off. I'm going to relook at some of our results now that we've filtered out the children out of this analysis. And if we look at our assumptions again, we still pass our normality. Homogeneity of variance, Levine's test. Did not update. Okay, so I just turned it back on and back up, and you'll notice that our standard deviations are a lot closer to each other. And you'll notice now that we pass, now that we have changed that, we actually passed Levine's test. And we're going to go look at our T, and now we would interpret the top line and look at these effect sizes. Look how big these effect sizes are. And this Bayes factor is now right close to 1 if we switch that. And as we saw from Navarro, a base factor of 1 is not real strong evidence for one or the other. And so if I were critiquing a study, I would just wonder of the, why they did the inclusion criteria the way they did. And I think the base factor lets us see that while we would fail to reject the null, there's not real great evidence here. And this may be a situation where we just didn't collect enough data to really understand what's going on, because there is a big effect size here. So there's definitely some kind of difference in ages as we look at this. And we now see actually that the negative screening group are older than the positive screening group. And so by trying to connect some of these dots, we really came up with some good questions on why would this kind of study be designed this way. And I would definitely, before I'm making any treatment decisions, I would go try and understand this. And this may be a situation where, maybe something just wasn't done as well. So we changed this. We have some questions now about how this would be. So I think just trying to connect those dots, trying to understand the story of your data, really helps you come up with good questions of, why is something a certain way? And there might be justifications for it, but we don't have any right here. So I would just, note these questions and then try to find answers before making any important decisions based on something like this. So we did learn a little bit about reporting some results, and we're going to try this again. So please help me report results of an independent t-test. Please report some relevant descriptive statistics first, followed by the name of the test performed and the null hypothesis, followed by the relevant statistical test information with the effect size, and interpret the results for the reader. Here is the relevant information. And so I went ahead and we'll just go ahead and do this again in ChatGPT. So if we copy, whoops, I want to go back, and I'll go to the original PowerPoint and copy that prompt. And paste it, and then I'm just going to hit Shift Enter, and that will let me go down to the next line. And we're going to copy this information out of our output. So if you right click on the table, we're going to hit copy. And if we paste that, and this does not paste like a nice looking table, but apparently ChatGPT can make sense of it. I'm going to hit Shift Enter to go down to the next line, and I'm also going to give it our assumption checks. So we right click on the table and copy, and then we can Control V to paste and hit Shift Enter to go down to the next line. And we have our homogeneity variance test. Copy. Hit Shift Enter to go down to the next line. And our group descriptive statistics. And okay, we have provided our basic output information to Jamovi, or to ChatGPT with that prompt. And let's see how it does. So we have some descriptive statistics there. An independent t-test was conducted to compare the mean age between negatives and positive groups. The null hypothesis states there is no difference in the mean age, while the alternative hypothesis states there is a difference. Our assumption checks, it went through and reported our assumption checks, that we met those assumptions. And here's our test results with a pretty nice, formatted correctly, and our effect size and our base factor and the interpretation. The results of the independent samples t-test suggest that the difference in mean age between the negative and positive groups is not statistically significant. The observed effect size suggests a large effect, but given the small sample size, the statistical test lacks sufficient power to detect a significant difference. The base factor near 1 further indicates weak or inconclusive evidence regarding the hypothesis. Although there is a numerical difference in age between the two groups, a lack of substantial significance suggests that we cannot rule out the possibility of difference due to random chance. Further research with a larger sample may help clarify whether this difference is meaningful. So, and this differs. I actually ran this one time before trying it out. The language is slightly different, but it picked up some nice points, and that matches pretty well with what we had looked at. Basically, I would have questions about these results, and I would kind of conclude that further investigation might be warranted based on that effect size. So you want to copy these interpretation, and then let's get Jamovi back up here and go to the bottom of your page, click inside the output till you get your cursor in there, and then paste those interpretations into there, because that's a great way that you can save this for later and not lose it. It's good to keep that. And this is something where as you're going through these output, you could add little notes, to yourself as you're interpreting things. There are a number of references here based on the tools that we use, especially with the adding in the base factor. But yeah, I think this was interesting that we could look at this example a little more and understand some of these ideas a little better. So I hope this is helpful. Answer the questions in Canvas and submit your output. So we're going to do, I would save this test as including your results, and then once you save that, then you want to go to export and browse to make sure you're in the right folder, and export PDF of your output. Go ahead and save that, and then you want to submit your PDF of your output in Canvas for your file. So have a good week, and we'll talk to you guys later. Excuse me.